Okay, moving on to geometric sequences now. So arithmetic sequences were obviously where one term to the next you had to add something. Okay, geometric sequence, you basically need to multiply by something. Okay, so 3 examples here. First one quite straightforward. You can see that we're multiplying by 2 to get to the next term in the sequence. Second one, we're multiplying by a quarter, and the third we're multiplying by -5. Okay, so it's still a sequence, but to get between them, for a geometric sequence, we need to multiply by a number. Okay, so we need to multiply the previous term by the same amount each time. Yeah, consider the sequence AR squared, AR cubed, right? That looks like it's come from absolutely nowhere, but that is a geometric sequence, because what's basically happening is we're starting with the first term A, and to get to the next term, we're multiplying it by something. To get to the next term, we're multiplying by that same thing, which is where the indices come in. Right, what you've got to be careful of here, indices are going to be a prominent part of geometric sequences. So if you have forgotten all your indices laws from National 5, then it might be worth looking back at them. Okay, so this is basically just that geometric sequence. We have a first term A. Okay, we're going to call it A because we've called it A in arithmetic sequences. To get to the second term, we take the first term U1 and we multiply it by some number R to give us AR. For the third term, we take the second term, we multiply it by R, in which case we take AR, we multiply it by R, and that gives us AR squared, and so on and so forth, until we get to a general term. UN will equal the previous term, UN minus 1 times by R, which would be AR to the power of N minus 1. Okay, and this is our general term for a geometric sequence, and it's going to be used quite a lot and is worth memorizing. Okay, I don't think it's in your formula sheet, so you need to know this one. So a general term in a geometric sequence is equal to AR to the power of N minus 1, where A is still the first term in a sequence and R is the common ratio, and that can be found by finding the kind of what we get when we divide one term by its previous term, and that can be done anywhere throughout the geometric sequence. Okay, so U2 divided by U1 is the obvious one, but we could do U3 divided by U2, U10 divided by U9, whatever it is. Look at the question and look at what's given to you to be able to find the common ratio. Okay, so first question up is a relatively straightforward one. So find an expression for the nth term and evaluate the 15th term of the geometric sequence 2, 6, 18, 54. Okay, so this tells us it's a geometric sequence, but we can quite easily spot that it is a geometric sequence because we're multiplying by something to get to the next term. Okay, it's not a common difference as in an arithmetic sequence. Okay, we have a kind of a common ratio. So the first term is definitely 2, and we can check the kind of the common ratio a couple of times. 6 divided by 2, 18 divided by 6, and even 54 divided by 18 all come out as 3. Okay, so our R value is just 3. So using the kind of the general term for a geometric sequence, UN will equal AR to the power of N minus 1. Okay, A is 2, R is 3, so our general term is 2 times by 3 to the power of N minus 1. So the 15th term will be 2 times by 3 to the power of 14, which is 9,565,938. Okay, don't try doing that on paper. You can stick that in a calculator. Okay, most of the time though, these aren't necessarily non-calculator questions, so you need to be careful. I think this next one would definitely be a non-calculator question. You can see there's thirds. I've already told you there's indices. So there's a lot of kind of National 5 going on here. Okay, so just make sure you're up to speed with all your surds and indices. Okay, but what we have here is we have a third term and a sixth term. So we don't have consecutive terms, so we can't instantly find R. We're going to have to take a slightly different approach for this one. But kind of write down what you've got. U3 equals 4 root 2 and U6 equals 16. Okay. General term is AR to the power of N minus 1. Okay, so in terms of the third term and the sixth term, we could say that U3 would equal AR squared and U6 would equal AR to the power of 5. In which case, we can substitute in the values that we actually know. AR squared is equal to 4 root 2 and AR to the power of 5 is 16. Right, that's all we've got to work on from this question. So we have to do something with this in order to find NRA and RR. Basically what we want to do is we want to combine these two together. Okay, the best thing to do is to divide them, because if we divide them, we'll get rid of our A and we'll get rid of a bunch of R's. But most importantly, we'll get rid of the A, and that'll give us an equation that we can work with that's just got the one variable. Okay, so if we do AR to the power of 5 divided by AR squared, that's going to be 16 over 4 root 2. But most importantly, as I say, the A's will disappear. So we get R to the power of 5 over R squared, which is again just your indices, just take them away as long as they're the same base. R to the power of 3 16 over 4 root 2 is 4 over root 2. Okay, right, we have to solve this. Basically what we're going to do is we're going to cube root both sides, but it might be easier to first of all rationalize the denominator. Okay, it just makes it slightly easier. It just means we don't have a fraction to work with. You can do it by just cube rooting both sides, but it's maybe slightly easier if we rationalize the denominator first. So it becomes 4 root 2 over 2, which simplifies to 2 root 2. Then we do cube root both sides. This is where it gets slightly more complicated. Okay, and we have to think of this in the most appropriate way. Okay, but we're dealing with this in terms of indices. Cube root basically means to the power of a third. Square root means to the power of a half. So we're going to put all of these things in index form. We have 2 times by root 2, and 2 is just 2 to the power of 1. Root 2 is 2 to the power of a half. So we're actually dealing with the same base here. And because we're dealing with the same base, we can actually simplify this a little bit better. Okay, in terms of index form at least. 2 root 2 is nice, but we want it in terms of indices to combine it with the cubed root. So 2 to the power of 1 times by 2 to the power of a half would be 2 to the power of 1 plus a half, which is 2 to the power of 3 halves. All to the power of a third, and as long as that's the case, we times those indices together, and 3 halves times by a third is just 1 half. So 2 to the power of a half becomes root 2, r is equal to root 2, okay? Long-winded, a lot going on there, okay, but it is just your indices. Technically a National 5 question, although obviously not really, okay? Right, so we've got our r, now we need to find our a. So we take our r value and we substitute it back into one of our first equations. Obviously the first one is slightly more straightforward, just because it has less r's going on. And we can kind of look and see the fact that we've got a root 2 for our r, and if we square it, then we won't have that root anymore. So a r squared equals 4 root 2. Now knowing that r is root 2, we can say that a times by root 2 squared equals 4 root 2. Root 2 squared is just 2, so 2a equals 4 root 2, in which case a equals 2 root 2. Right, so what we actually have to find here is the nth term. So we need to put all this into our general formula. Okay, so un equals ar to the power of n minus 1, in which case we get 2 root 2 times by root 2 to the power of n minus 1. And we want to simplify this as much as we possibly can. Right, because we've got a couple of root 2's there, okay, we can do this in terms of root 2. So what we should have here, what we basically have, and this is where you need to be a little bit clever, 2 is just the same as root 2 squared, okay? So what we actually have here is we have root 2 squared, I'll write this up here, root 2 squared times by root 2 to the power of 1 times by root 2 to the power of n minus 1. And obviously the reason I'm doing this is so that we have all the same bases. Root 2, and root 2, in which case if all the bases are the same, we just add the indices. 2 plus 1 plus n minus 1 is going to be n plus 2. So we have root 2 to the power of n plus 2. There are different ways of writing it, but that from what we started with is probably the simplest way. Not the prettiest of questions, okay, unless you like this kind of thing. But yeah, it's a lot of what we did in National 5 in terms of surds and indices, just a bit more extreme, I guess, okay. Right, one more, slightly different one this time. What's the first term in the geometric sequence 2, 4, 8, 16, 32 to exceed 500,000? Okay, so a couple of things here. You need to know what 500,000 is. And yeah, you need to kind of take everything that you've got from the sequence that's given to you to be able to find that. So we know the first term. The first term is 2. We can see the common difference. The common ratio is just 2, in which case we have a general form. Un equals ar to the power of n minus 1 would be 2 times 2 to the power of n minus 1. We want that value to exceed 500,000. So we want 2 times 2 to the power of n minus 1 to be greater than 500,000. And then we're basically just working this through to find n. Right, savvy ones of you will realize what we're going to need to be able to do this. Because that n is a power, I don't want it to be a power. I can't do anything with it as it's a power, and in which case I need to kind of bring it down. To do that, I need logs. So divide both sides by 2 and then take the log of both sides, okay? So we've got 2n to the power of minus 1 is greater than 250,000. And to find n, I need a log of both sides. Doesn't necessarily matter what log you take, but it's perhaps easier to work with log of base e. So we have now, using our laws of logs, so now bringing a bit of higher, n minus 1 times by the log of base e of 2, that brings the n down, which is what we want, is greater than the log of base e of 250,000, okay? And then dividing both sides by log of base e of 2, n minus 1 will be greater than, yeah, all of that, in which case you can just shove that straight in a calculator and then add on the 1 to find our n value to be 18.935, in which case the first term that is greater than 500,000 will be the 19th term. Okay, so what we're basically finding here is we're finding the exact term or the exact kind of value within that will be greater than 500,000. Okay, but we want the first term, so we want the 19th term, the next term in that sequence. So a kind of a wee variety of different geometric sequence questions to get you going just now. But you can see the main thing you're going to need here are surds and indices and even a little bit of logs.